So, hi everyone. So today I'm gonna try and help any one of you to understand, or maybe understand a little more, the concept of time that is slightly complex in GStreamer. So it's a take two because if for the ones that were there in 2013, 13? No, 16? Yeah, in 13, yeah. Edward did a talk about the same subject, actually, with the same title. But I thought it was about time to just bring it back and refresh people's memory. It's a bit about me. I work at Collabora. It's been there for almost 6 years. I'm new dad, so that's my new job right now. And whenever I have some time left, I do GStreamer development. So he's Malik. He actually he's a good programmer. He really likes typing, actually punching on the keyboard. So what we're going to talk about today. So we'll try to figure out to explain my view of what is time in GStreamer, because time is kind of a vague thing. We'll go over where the time is presented in GStreamer, where it is exposed. Then we'll figure out that these times are not all the same scale, the same point in time. We'll see later. So we'll talk about the classification of time in GStreamer. Some of it is already in the documentation, some is not. Maybe it would be good to do an exercise of updating the documentation afterward. We'll also have an overview of how to synchronize the with time in GStreamer in an element. Which time to use actually to synchronize, and finally we're looking at a big question, something that comes back all the time, is how do I craft a timestamp so it works in GStreamer. So let's start with what's the time. So I picked a definition. There's I don't know. There's hundreds of definitions of time over there. So I could have picked anyone, but this one was very short, simple, and it covers the use cases in GStreamer. So the point of or period when something occurs. That's pretty much it. What occurs while we're playing back audio and video, or displaying subtitles. It could be a point or a period. So the duration is a period, and a timestamp is a point. So I think it fits well, except that it doesn't mention that time is relative. So time is relative to the speed of playback. Time is relative to epoch, or I don't know, the common era, or could be relative to many things. So if you speak about 10 years as a point in time, well, you need to define where it started. Otherwise, you have no idea. So, oh, and I forgot to start my timer. That's going to be useful. So yeah, where is the time presented in GStreamer? So first, we'll just do a quick overview of where is the time. I'm going to explain what is those times, but I'm not going to go further. We'll see it later. So if it wants to change page. Hello. There we go. No. There we go. So, one obvious places where you'll find the time is in the GST clock. Unlike what most people may think, the clock actually have two times, the internal time and the slave time. If it's a master clock, there's only, those are the same actually. And if it's a slave clock, you'll have two times. You'll have the internal time and the useful time, the one that is translated. You'll find some notion of time in the GST element. The start time, which you'll read the documentation as being the time you went to pause state. And the base time, which is the time you went to playing state. That works. There's also times you can query. So you can query the position, which is actually the position in your stream. So if you have a 5-minute video, you could be at minute 2. That's a position. The latency. The latency is how much time your pipeline is waiting in order to be able to synchronize your different streams, audio, video, etc. And finally, the duration, which is just like the position, but it's how long is your stream. You'll also find the notion of time, and you probably already know, in buffers. So presentation timestamp, not really the presentation in that sense. It's a tool, it's an information that can be used to figure out when to display, to present actually. But it's just a random point in time. Decoding timestamp, which is a special case for when you have reordering, encoding that cause reordering, and the duration of that buffer. You'll also find a lot of notion of time in the GST segment. So the rate, it's the playback rate. So I'm playing 2 times faster or something like that. The applied rate, this is for a special case where your server, let's think of an RTSP server, will transcode the stream for you at double speed. So in fact, you're just playing normal speed, and the server is playing double speed. So we need that information to be able to figure out where we are in the stream. Base and offset, that goes together. So it's used to calculate basically when the segment has started in a certain scale. We'll see later a bit more about that. I don't want to mention too much. Start and stop, it defines the lowest and the highest value time. One of those timestamps can be. It could be before, in fact, but let's keep it simple. Let's say it's defined the biggest and the smallest BTS. But if you have a DTS, DTS could be before the start. The time, it's simple. It's defined as the stream time at start. And finally, the duration of your segment. So those are times. Now, there's a lot of times, and all those times don't correlate easily together. You need to understand the relationship. Otherwise, it's not very useful. So let's classify the time. In GStreamer documentation, you'll find these 3 types of time. But I'm adding one more today because otherwise, I can't really explain you everything, every relationship between buffers. So, and the name of this one, I didn't discuss with anyone, so don't take it as like the final definition. Maybe we'll find a better name. So the stream time, this is the position. This is basically a representation of the position in your stream, in your media. So as I said, if you have a 5-minute media, so it gives you the point in time. It's affected by the speed of playback. So if you're playing faster, well, stream time will go faster. If you're playing slower, stream time goes slower. It also applies actually in stream time in the idea of duration. The duration could be in the stream time scale. The running time, this is actually the time that has been spent in playing state. So I'm saying playing state. It means that it doesn't progress when you're in pause state. So this is actually always aligned with the clock time. It's the same scale. But it always starts at 0. So the point in time is 0 when you went to playing the first time. Finally, you get the clock time. So GStreamer on the pipeline, there's a clock, and that's the time you read on the clock. The point in time it starts exists, but it's undefined. It doesn't mean anything. So that's why we need something like running time to create a base time to be able to make sense. The clock also has the capacity. Some clocks will keep running in pause, and some clocks won't. So the running time is here to actually compensate for that deviation in clocks. So a good example, most audio clock are derived from a running ring buffer. So when you're not playing, the ring buffer is still, and the time is not moving. Finally, there's the buffer time. This one is actually should actually have been aligned with the stream time, but at some point, I don't know when, in GStreamer, we introduced the applied rate. So the buffer time, at that time, when you have the applied rate, you receive a stream, and the timestamp in the buffer have been adjusted by the server. So the buffer time is no longer stream time. So your timestamp are in a different scale, basically. So we need to keep in mind that buffer time is a concept that is not really defined or documented. It's not something you can calculate through the GST segment, but it exists. Here. So those are the classifications. So that's the original documentation. That's how we show people how the clock works together. The example is great, but it's not very realistic over what we do in GStreamer. Let me explain. So here you got the clock, which is great. It's a random point in time. You don't know where it starts. And then you got the running time that starts at 50 there. So it starts at 0 and it progresses. You're playing all the time. There's no pause in that graphics. So we're already not covering many use cases. Finally, you got a stream of 10 milliseconds that we play till the end. And then we're going to replay the last part, this little part. Ooh, I need to be careful. Again, by doing a non-flashing seek over there. Doing such a non-flashing seek is super hard in GStreamer, by the way. You need an extra thread, it's really hard. But that's the example we had. But it's good because you see that the stream time is really the position in the stream. You see that when you seek, the stream time just resets, so it goes down and back. And so it's quite interesting there. Now, I created another graphic. It's not complete either. I would need like 2-3 walls to actually cover all the use cases, but we'll try to make a good graphic over time. In that graphic, I wanted to represent here in red the master clock. So it's a master clock that doesn't stop actually while you're in pause. That's in this column we're in pause. I'll explain why later. Then you got a slave clock just as a representation, which would be an audio clock. So audio clock are well known to be quite off. As you can see, the slope is not the same. And it actually stops during pause. And finally here in blue, I'm representing the running time. So it's the time spent in playing. And finally, the stream time. So what happens here is that we start playing. So you see that the master clock, the running time, and the stream time are all going together. Normal speed, rate 1, it's all the same scale. At some point, I decide to do a flushing seek. As Sebastian explained yesterday, when you do a flush, actually on GStreamer, you lose your state and you go back to pause for a while. So during that period, what happens is that both, running time and stream time will stop progressing. So the offset between the clock and the running time actually changes. It increases. And because I'm doing a 0.5, an in-place actually 0.5 speed seek, you can see that the slope of the stream time actually is lower, is going slower. And that's where it diverges. And that's where you start seeing that, no, running time is not the same thing as the stream time here. You see it's a different scale, so you need to translate it. That's where it gets interesting. So let's go back to our time in GStreamer and let's classify it. So internal time, well, we don't really have a classification for it. It's some sort of clock time, but it's not scaled. It's in some other scale. And we slave that anyway, and the GST clock object gives you all the tools to do the translation. I think the API is quite evident. We don't need to go over that. And then the slave time, unless it's the master clock, is the clock time. In GST element, start time is running time. Because if I could just go back, you see that it's the running time is something that starts at 0. And the start time always starts at 0, so and it's on the same scale as the clock time, while the base time is a position, like on the first graphic, on the clock. So, see, it's easy to confuse things because, see, those two numbers look like they go together, but in fact they're on different scales, so you need to be careful. Not scale, but they're on different start position. Then the time you query, the position is stream time. That's kind of obvious, and the duration goes with the position. It's stream time also. And the latency, well, it's running time or clock time. It's on the same scale, and it's a duration. So it's hard to say if it's running time or clock time, but let's say it's about the same thing. If we classify in the GST buffer, this is all buffer time. which is most of the time in the scale of the stream time, but sometimes it's not. If you look at the rate, so this rate lets you convert from stream time to running time, or the opposite. The applied rate is a rate between buffer time and stream time. Base and offset, the base is actually in running time, but the offset is in buffer time. Just as an historical aspect, everything in GStreamer in terms of time is an unsigned integer. So there's a lot of complexity that has been added to avoid going above 0 because it creates big number. And the offset gives us the ability to have a stream time or a running time that goes negative, mostly, that goes backward. So you can actually offset backward the running time or the stream time, I don't remember. But anyway, that's about what it does. That's why they go together. But they're not on the same scale for mathematical reason. Start time, stop time, this is buffer time. The time here, which is the start, it's the stream time at start. It's defined as is, so that's easy. And duration, this is in buffer time. This is really the duration between start and stop in the case where you don't know stop. It's mostly used by demux search, but it's not something very important. Now, as we said, start time start with 0. Sebastian asked yesterday too, so I could expose actually how it works, this calculation of base time and start time. But remember one thing, the only thing that matters for you in your work most of the time is the start time. The base time is mostly the element memory. It's to be able to keep track of the running time. So when you go to pause, the start time is 0. Because running time starts at 0, right? Then later, when you go to playing, you want to set the base time. The base time is a clock time. So it's going to be now minus 0. So it's going to be now. It's going to be a time on the clock right now. Eventually, you'll go to pause. And then we will save the moment we went to pause. So now, minus base time. This formula, I like you to watch it right now, because this is the only formula that exists to calculate basically the running time. So at all moments when your pipeline is playing or live, you can calculate you can define actually what's the current running time by taking a time on the clock and subtracting with the base time. There's no magical math. At this point you're in pause, you saved the moment you went to pause in the start time, and you saved it in running time. And when we go back to playing, we take the moment on the clock now, and we subtract the saved start time. What it has as an effect is that it brings back the base time, so it increased the offset, and it's exactly like what we saw on the graph before. So this way you ignore the time you spent in pause in the running time. Your running time will only represent the time you spent in play. So, what time should we use to synchronize? So, well, the most obvious time to synchronize is obviously the clock time. And the most important case in GStreamer, especially for playback, is what audio and video sync do, actually the base sync do. So, synchronizing on the clock time require multiple steps. And actually what happens is that you get a segment that travels to your sync. And then eventually you get buffers that will reach there. From the buffer time and the segment, you're going to convert to running time. And then from that running time, you can offset to your clock. And then you can ask the clock object, could you wait until that moment? Obviously, to that, you also need to subtract your latency, because sometimes you need to send to your hardware earlier so it reaches the light or it makes sounds at the right moment. But that's as simple as this. The code is quite complicated because there's many use cases induced by state changes, the fact that the integers are not signed, the fact that the rate could be backward, forward. So calculating time requires a lot of ifs and else condition. But fortunately, this is mostly enclosed into the GST segment API. Now, I'll go in further detail on these. If you look at mixers actually, they do a mix of synchronization between using a clock and using the running time. So if it's non-live, it's only going to wait for data to come and look at the running time of that data, and then it will sort it, or if it's the same time, it will merge it, and then it will produce this data, and that's it. But if it's live, it means that one source could stop producing, or there could be a gap or a loss or something. So the mixer will receive data on all its pad, but oh, there's data missing from that source. So at that moment, it's going to it's going to use the clock to wait until the last moment that you can actually produce data. And at that moment, if there's no data that's coming in, it's going to conceal that and just produce a packet. So concealment of data in this case depends on the mixer and the media type. In maxers, well, right now maxers only do synchronization on running time. So whenever they receive buffer, they convert their time to running time. So all the buffers from every sources are correlated together. But that's it. So if a source in a live maxers right now stop producing, well, the maxer is stalled. So long term, we're looking forward also using the clock like we do in the mixers. And fortunately, we have a base class for that now, which is called GST aggregator. There's other type of synchronization. One example is a project I did this year, a small project. I integrated the WebRTC DSP library. And in this case, you have echo canceling. So you have a speaker that speaks into his microphone that sends data over the wire. And then somebody also speaks in his microphone, but the microphone hears both the incoming voice and the person that speaks voice. So you need to kind of remove that from the feed that goes over here. So what we do in GStreamer is that we actually watch for the data that arrives from the network, creating a small observation queue in the past. And there's a delay until it's going to be played, and the DSP will read from that pool of data and try to remove the echo, basically. But to do that, whenever you get data from the source, you need to find actually, you need to synchronize in the sense that you need to find the matching data from the echo data. So that's another type of synchronization. It's also done in running time in this case. So running time is a very important scale. So how do we effectively synchronize? So in sync, as I said, you will transform your PTS or whatever you have, because there's a preference of DTS over PTS when you synchronize an element. Like if it's encoding data reaching the sync, you want to use the DTS because the PTS could be reordered. So for synchronization, it wouldn't make sense. But for this example, I've used the PTS. So you transform it to running time. You have this little function. It's magical. It does everything. And then from there, you can calculate your synchronization time, which is your running time plus your base time minus your latency, like your specific element latency. Because if you were to just send at that time the data, it would be that time, that duration late. So you need to send it earlier for your hardware to catch up. Unless you have specialized hardware, which is callback based or something, it makes everything more complicated. And then this is optional, you could use a function like GST base sync wake clock. But some people would prefer an asynchronous function, some element will need to use the clock directly. That's really something that you'll have to be specific. But I'm just pointing out that there's API to help you do that. And they actually help you correct the errors like the jitter or stuff like this. So watch carefully, there's always. For midstream, like the mixer for midstream synchronization, it's basically the same thing whenever you want to use the clock, with the exception that the latency cannot be like the entire pipeline latency. It doesn't make sense. So we have defined over the development of GST aggregator, we hope it's right, that the last moment you can produce data in a live mixer or an element that's synchronized in live, identity is included, is basically the latency reported by upstream elements, upstream from yourself. So what those elements will do is that they will run an extra latency query just to be aware of just the part that is upstream of their elements. So it means there's more latency query running. But yeah, so far this seems to be the right assumption, but probably there's a lot of studies to do there to be sure. For synchronization data, well, you need to take into consideration much more elements, but you don't need to watch the clock. So when you receive echo data, there could be drift, there could be buffering delay, there could be packet loss. So this is just like echo data, there's a gap over here, then you have more echo data. Well, that makes no sense, it's too far ahead, but anyway. And then you can see that the echo data arrives with a delay, so it's before. In the case of WebRTC, you actually tell the stack what's the delay and you keep sending. So the buffer inside WebRTC DSP actually is fed in advance. So they know about the echo before it actually have to cancel it. But that's basically it. But we don't really handle those cases. Like, it's quite a simplistic implementation. But it gives you an idea that the goal is to find, for a certain delay, a point in time that matches the capture. You clip the part that makes no sense. Why there would be a part that is in the past? Well, you could start receiving on a network before you start recording. That happens all the time because capture is slow, it takes time. And so most of the time it's the other calling, so he's already ready to send the audio. Or because of the drift. At some point, you've drifted too much and you just want to skew that data. Depending on your echo canceller, because this is WebRTC DSP, it's like a magical echo canceller. You can do anything, it still works. You might need to resample or do very, very cool stuff there. But anyway, with data, you just need to pick for your capture a piece of data that makes sense for that. And then you can combine and do your operation. That's data synchronization. So that's cool. So now we mostly know the concepts of synchronizing in GStreamer. We didn't have time actually to go in detail and how to really program that, but just keep in mind those concepts. It will build up your expectation whenever you have to read code in GStreamer and figure out how it works. Then it's always interesting to know how to produce timestamps. So very often you create an element, an app source as an example, and you need to put timestamp on your buffers, but you don't really know how. Well, I don't have a magical answer for you, but there's multiple ways you could create valid timestamps. And there's multiple ways you could create wrong timestamps. So one of the very common cases is that you have an app source and you have a live pipeline. So pause state make no sense, buffer duration or anything make no sense, and you most likely know the latency or you hard-coded it. So you can basically say, fine, whenever I got the buffer that I want to queue in GStreamer, its timestamp is the running time, the current running time. Like rate is 1, it's like a bunch of assumption. Rate is 1, applied rate is 1, I have no latency, and that's it. That will work for many cases, and especially it will work well if all you wanted to do is image processing. So this is just way enough. In other cases, the non-live cases with something like an app source, you can also make it simple. Start with 0, so you can use the default segment, and just say, okay, all my buffer have that duration, and the timestamp is the last plus the duration. So those two are, like, in simple use cases, the most common timestamp crafting. And it works with the default segment produced by things like app source. In real world, you most likely have a clock. So your software, your library, or your hardware is provide you a clock. So you'll create an instance of GST clock. And then you will use if you manage to provide it to the pipeline or slave that clock with the master clock. And all you'll have to do is take your hardware timestamp, ask the clock to translate it to your master clock, and that's your timestamp. Well, not exactly. You then need to produce a segment that will define properly the start time and the stream time at start, actually. So you need to set the start at the minimum. You could set you can leave some of the field onset in GST segment, and then you set time, which defines if you query the position, it defines what is going to be displayed. So that's rather important. This is incomplete, I know, but it gives an overview of method to just create timestamp. As you can see, the math are not very complex. It's always A time B plus C, and anytime there's a multiplication and scaling, there's actually a utility in GST segment to handle it. And the overflow. So that's it. Any questions? Crystal clear. Yeah.
Just a comment that GStreamer does have the GST test clock. So if all this is a bit confusing for some, being able to craft either use your element or a little pipeline and being able to manually advance the clock and see its impact. At least it's helped me a lot to understand what is going on.
So for those that don't hear in the back, Harvard was saying that GStreamer has a GStreamer test clock. I think it's a clock that you crank or something.
Yeah,
So a lot of people think it's impossible to test the timing. Well, in fact, if you control the clock, it is quite possible. So the test clock is a clock that you can actually you can make it progress by yourself. So you can actually trick your code into progressing to a very specific point on a very specific race condition just by yourself. So yeah, whenever you develop stuff and you start having synchronization issue, test clock is a fantastic tool. Anything else? Yep.
Thank you for your presentation. I want to ask about applied right member inside the GST segment. So when you call seek function, you can pass the rate, but who's responsible for setting applied rate?
Okay. So just to resume, the question is, who's responsible to decide for what is the applied rate? And if I understood the question properly, the answer is the source. And it knows because it's bound to whatever protocol is being used. The only source I know that actually defines the applied rate is the RTSP source. And you'll find in the RTSP metadata this information. So you just need to take the scale factor, translate it, put it in the applied rate.
So it mostly coming from outside, from server.
Yeah, it's really for RTSP that it was added, and for the case where you have a transcoding server, which you need a lot of CPU or a lot of performance there. But yeah, if you have a transcoding server. Anyone else? Well, thank you very much. And